In 1911, crawler excavators sank in coalfield mud, and entire mines stalled. Inventors tried tracks, but those solutions failed. Oscar Martinson patented a walking machine that could lift 80% of its own weight and step 7 feet at a time. That mechanical leap made giants like Big Muskie, 14,500 tons, pressing just 44 pounds per square inch, walk where no machine had survived before, and dominate mining for decades. But what triggered this desperate turnaround? And how did a simple dual shoe idea rewrite earth-moving history before hydraulics arrived? Spring 1911. Coal mines across the Midwest ground to a halt as tracked excavators, once hailed as the solution to earth moving, vanished into the muck. Operators watched helplessly as tons of steel and iron crawlers sank axle deep in soft overburden, engines straining against a sea of mud. Some machines stalled so completely that crews abandoned them where they sat, half buried. Tracks caked with clay, booms jutting at awkward angles. Field supervisors scribbled incident reports, delays stretching for days, lost production, mounting costs. Timber mats and gravel fill offered little relief. Each attempt to rescue a stuck dragline risked more equipment and more men mired in the same pit. The problem was not just inconvenience. It threatened the entire economics of surface mining. Mines faced shutdowns, payrolls hung in the balance, and the promise of mechanized progress seemed to dissolve with every rainstorm. The crawler craze that swept through the industry had hit a wall of mud, and engineers were under pressure to deliver a machine that could move, dig, and survive where tracks simply could not. In the heart of this crisis, a new idea was about to take shape, one that would challenge the very notion of how a giant machine could cross a coal field. Oscar Martinson filed U.S. Patent 1,101,460 in January 1913, introducing a solution that changed the fate of surface mining. The patent diagrams show a pair of massive steel shoes, each suspended from a horizontal shaft running across the base of the dragline. At the heart of Martinson's design sits the eccentric cam, a wheel set off center on the shaft. As the shaft rotates, these cams force the shoes down to the ground, transferring the machine's weight from the body to the shoes. The mechanism does not drag or roll. Instead, it lifts the rear of the machine, then slides the entire structure backward in a single motion. Each cycle moves the dragline a full 7 feet, an extraordinary 7-foot leap for a machine that weighed dozens of tons. The dual shoe system ensures that while one shoe bears the load, the other resets for the next step, creating a stable, alternating rhythm. This purely mechanical process, described in the patent claims, allowed for continuous walking without the need for tracks or wheels. The invention's simplicity lies in 2 shoes, 1 shaft, and a precise sequence of cam-driven lifts and slides. Martinson's breakthrough did not just solve the immediate crisis of bogged-down machinery. It delivered a new way for excavators to move across the softest ground and set the stage for the first working prototype. The first Monighan prototype rolled onto test ground in spring of 1913, its steel shoes gleaming with fresh machine oil. Operators engaged the horizontal shaft, sending the eccentric cams into motion. As the cams rotated, each shoe pressed firmly into the earth, shifting nearly 80% of the machine's weight away from the main frame and onto the shoes themselves. The dragline's rear lifted cleanly, and the entire structure glided backward in a controlled 7-foot stride. Engineers noted in trial logs that, unlike crawlers, the shoes did not dig in or deform the surface. The pivoting slideways built directly into the shoe mounts allowed a float of 6 to 8 degrees, letting each shoe adjust to uneven ground without risking a tip or a jam. This lateral give was critical, because it meant the machine could walk across rutted coal fields and soft overburden without binding or stalling. The prototype's success was not theoretical. Every step delivered proof that Martinson's design could carry immense weight, maintain stability, and keep moving where tracks failed. Within months, Monighan began scaling up the concept, confident that the walking mechanism had passed its first real-world test. Not in a drawing room, but in the mud and grit of the coalfields. Steel shoes, eccentric cams, and a 7-foot stride define the walking cycle of a dragline excavator. A horizontal shaft, typically turning at 1 or 2 revolutions per minute, governs each phase of the cycle. As the shaft rotates, the eccentric cam profile presses the steel shoe downward, shifting nearly the entire weight of the machine, sometimes over 7,000 tons, onto the shoe's broad surface. This force is dynamic. It peaks during the initial downward drive, where contact pressure can momentarily approach the cam's maximum bearing load, estimated in the range of several million newtons for the largest machines. Shaft rotation divides the cycle into 3 clear phases. The first phase is the lift. As the cam rises along its oval track, the shoe pivots downward and the machine's rear elevates. At that instant, ground reaction force surges, with up to 100% of the dragline's mass pressing through a contact patch that can span 14 by 70 feet. Lift gives way to the slide. During the slide, the cam wrist pin guides the shoe horizontally along a slot, and the entire machine glides backward. The force vector shifts from pure compression to a combination of shear and rolling resistance. The shoe's pivoting slideway, engineered for 6 to 8 degrees of lateral float, absorbs uneven ground, distributes stress, and prevents sudden spikes that could fracture steel or deform soil. Reset completes the step. The cam rotates past its apex, lowering the machine back onto the main frame, while the shoe swings forward to prepare for the next step. Dynamic models show force peaks not only at initial shoe contact, but also at the transition from lift to slide. The cam geometry, its offset radius and oval track, controls the timing and magnitude of those loads. Force cycles on a Marion 8950 show repeated high compressive loads, alternating with lower loads as the machine resets. Each revolution of the shaft, each 7-foot step, repeats this pattern hundreds of times per mile, 754 steps to be exact. The slow cadence and massive forces place unique demands on cam bearings, shoe pivots, and the steel itself. Stress maps, built from patent diagrams and field measurements, reveal concentrations at the cam track interface and at the leading edge of the shoe during the slide phase. Engineers track these patterns to predict wear, refine cam profiles, and select bearing materials that can survive decades of punishing cycles. The objective is not only to move the dragline, but to distribute forces so efficiently that even a 14,500-ton machine presses on the earth with less intensity than a family sedan. This careful balancing act, managing millions of pounds with every cycle, explains both the longevity and the mechanical challenges of the walking dragline era. Bearing surfaces inside a walking dragline endure relentless punishment. Every step channels millions of pounds through a handful of critical contact points. To keep these giants moving, maintenance crews developed a culture of vigilance and routine, where missed lubrication or a delayed inspection could mean catastrophic downtime. Marion power shovel engineers specified a network of grease lines feeding each cam bearing and shoe pivot, and operators trained to monitor flow meters and check for pressure drops. Grease reservoirs were sized for extended cycles, and every shift crews walked the length of the machine, feeling for heat at bearing caps and logging each point in maintenance ledgers. The main walking cams, sometimes loaded to over 8 million newtons during peak lift, depended on a film of lubricant a fraction of a millimeter thick. Without that film, metal-on-metal contact could raise surface temperatures high enough to alter steel microstructure, risking cracks or galling. Heat and surface condition were constant concerns. Sensors mounted near critical bearings provided early warning of rising temperatures or vibration spikes, prompting shutdowns for re-greasing or adjustment. These alerts were not theoretical. They prevented failures that could halt production for days. Cable systems demanded equal attention. The main hoist and drag cables, often 5 inches in diameter, cycled through thousands of load reversals as the bucket dug and swung. Each cable followed a strict replacement program, with lifespans tracked in hours and cycles rather than months. Crews inspected for broken wires, core fatigue, and strand separation, using magnetic flux detectors to catch invisible flaws before they propagated. A single cable break under load could snap steel like twine, endangering both machine and crew. Scheduled replacements were non-negotiable, even if cables still looked serviceable to the naked eye. The inspection cycle for a walking dragline became a ritual. Every 10,000 walking steps, each cam, shoe pivot, and cable anchor underwent a detailed check. Bearings were pulled and measured for wear, with any deviation from specification logged and addressed. Field studies on Marion 8950s showed that with disciplined care, cam bearings could survive well beyond the 10,000 cycle benchmark, sometimes lasting decades before requiring overhaul. Yet the limits were always practical. Even with the best maintenance, the combination of load, grit, and time would eventually wear down metal. When that happened, crews swapped out worn bearings or machined new bushings on site, returning the machine to full strength in days rather than weeks. The longevity of these machines rested not on indestructible parts, but on relentless attention to detail. Maintenance crews became the lifeblood of the walking dragline, anticipating problems, catching early signs of wear, and turning scheduled downtime into a science. Their work ensured that a 7,300-ton Marion or a 14,500-ton Big Muskie could keep walking for decades, one 7-foot stride at a time. A Marion 8950 dragline stands taller than a 10-story building, its boom stretching 310 feet, longer than a football field. Each shoe measures 14 feet by 70 feet, and together the shoes cover 1,960 square feet. That is larger than a suburban house, yet both shoes must support the entire weight of the machine as it walks. 7,300 tons, balanced on 2 slabs of steel. When the cams lower a shoe to the ground, the contact area spreads the load so evenly that the pressure beneath the shoe averages just 44 pounds per square inch. For comparison, a typical car tire presses down at 30 to 35 pounds per square inch. The paradox is plain. A 7,300-ton dragline steps more gently on the earth than a sedan rolling down the highway. The math behind this is simple but powerful. Take the full weight of the dragline, 14,600,000 pounds, and divide by the total bearing area of both shoes. The result is a pressure that seems almost impossible for a machine of this scale. Even Big Muskie, at 14,500 tons, managed to stay below 44 pounds per square inch, matching the Marion's gentle touch. This is why walking draglines could cross soft overburden that swallowed tracked machines whole. The massive shoes, shaped like elongated rectangles, acted as snowshoes for steel giants. Ground pressure is not just a number on a chart. It is the difference between progress and disaster. In the coal fields, a few extra pounds per square inch could mean the difference between a machine gliding forward or sinking axle deep. Operators and engineers obsessed over these figures. They measured shoe area down to the inch, recalculated pressure after every major repair, and watched for signs of rutting or soil failure beneath the shoes. Even with the advantage of such a low pounds per square inch, crews sometimes built timber roadbeds for the largest drag lines, adding another layer of insurance against the risk of sinking. The shoes themselves were more than flat plates. Each was engineered with a slight curve and a pivoting slideway, allowing up to 8 degrees of rotation to match the contours of uneven ground. As the cam pressed down, the shoe could tilt and adjust, keeping the pressure distributed across the full area. This design prevented edge loading, where too much force at one point could punch through the soil. The result was a machine that could walk across muddy, unstable terrain with a footprint lighter than a city bus. These statistics are not just technical trivia. They explain how walking draglines became the kings of surface mining. The paradox of 44 pounds per square inch, lighter than a car, yet carrying more mass than anything else on land, turned physics into a practical solution, allowing machines like the Marion 8950 and Big Muskie to move where nothing else could. Each stride, each calculation made the impossible routine. The numbers became the language of survival in the coal fields, and the reason why these machines could walk at all. Inside the cab of Marion 8950 walking dragline, the world shrinks to a cockpit perched 200 feet above the ground. The cabby feels cramped and precise. Operators climb a narrow steel staircase, boots clanging against each rung, until they reach a control room with windows facing the endless cut of the coal pit. The cab sways slightly, even at rest, reminding everyone that this is not a building, but a machine balanced on 2 steel shoes ready to step at the operator's command. The controls are not simple levers. The controls are a bank of wheels, foot pedals, and toggles, each linked to a separate function: hoist, drag, swing, and the walking gear itself. Operators learn to read the subtle feedback of each system: the vibration in the floor, the pitch of an electric motor, the tension in the cable as the bucket bites into overburden. A mistake with the drag cable could snap a 5-inch wire rope, while a slip during walking could tip thousands of tons onto an uneven bench. Training is measured in months, not days. 6 to 12 months under the eye of a seasoned operator, practicing first with empty buckets, then with live loads, until every motion becomes second nature. 2 modes govern life in the cab. Digging mode demands focus. The operator lifts the bucket with the hoist cable, swings the boom into position, and drags the load across the pit floor. Each movement is coordinated with spotters on the ground, relayed by radio or hand signals. The goal is efficiency. Move as much earth as possible without overloading the machine or risking a cable break. The rhythm is relentless: hoist, swing, dump, reset. Every action is deliberate. Every second counts toward the day's tally. Walking mode is a different test. The operator shifts attention to the walking gear and engages the horizontal shaft that rotates the cams. A glance at the instrument panel confirms the load has transferred to the shoes. Now the cab tilts gently as the rear of the machine lifts off the ground. The operator watches for any sign of imbalance: a sudden jolt, a change in the sound of the cams, a warning light on the panel. The entire dragline slides backward 7 feet, then settles as the cams complete their cycle. Each step is slow, measured, and irreversible. There is no room for error. A misstep could mean hours of recovery, or worse, a machine lost to the mud. Manuals from Marion Power, Shovel, and Bucyrus, Erie spell out the procedure in detail. Operators are instructed to monitor bearing temperatures, check cable tension, and keep a log of every walking cycle. The learning curve is steep, but the payoff is clear. Operators skilled in both digging and walking command the highest wages on the crew. Their expertise keeps the machine moving, the pit advancing, and the coal flowing to the surface. From the cab, the scale of the operation is both humbling and empowering. Below, ground crews look like ants, dwarfed by a machine that can move more earth in an hour than 100 men with shovels. Yet every motion depends on the operator's judgment. The walking dragline is a giant, but it only moves when one person, high above the pit, knows exactly when to dig, when to walk, and when to wait. In the autumn of 1967, the first shipment of steel for Big Muskie's frame arrived at Central Ohio Coal's sprawling assembly yard. Flat cars stacked with girders, boom sections, and machinery parts stretched along the siding, each piece tagged and cataloged for a construction effort that would demand 2 years and 200,000 man-hours. Crews from Bucyrus, Erie, and local unions converged on the site, their numbers swelling into the hundreds as the scale of the project became clear. The initial phase focused on laying the foundation, a reinforced concrete pad poured and cured to anchor the turntable that would support nearly 15,000 tons of machine. Surveyors checked tolerances to fractions of an inch, knowing that even minor errors could throw the entire superstructure out of alignment. The lower works took shape first, with welders and riggers assembling the massive base ring and roller circle. 128 rollers, each weighing over a ton, were spaced precisely to bear the rotating upper works. Cranes lifted prefabricated segments into position, inching them together with hydraulic jacks and steel pins. Each lift was a calculated risk. The largest boom sections tipped the scales at over 100 tons, requiring synchronized crane teams and signalmanton to guide them into place. Assembly logs from the winter of 1968 describe night shifts spent aligning the shoe pivots and cam housings, torches hissing in the cold as crews worked by floodlight to keep the schedule on track. By spring, the central machinery house rose above the pit, an armored shell housing 18 electric drives, each rated at 1,000 horsepower. Electricians threaded miles of cable through conduits, wiring control panels and power distribution systems to handle 13,800 volts that would feed Big Muskie's appetite. The walking mechanism, built around a pair of horizontal shafts and eccentric cams, arrived in sections and was assembled on site, each cam weighing nearly 20 tons. Fitters installed the 14 by 70-foot steel shoes, bolting them to pivot frames engineered to allow up to 8 degrees of lateral movement. Every bolt, weld, and bearing was inspected, logged, and signed off before the next phase could begin. The boom, at 310 feet, was longer than most city blocks and presented the greatest logistical challenge. Sections arrived by special convoy, escorted by state troopers along rural highways. Erecting the boom required a custom-built derrick and a ballet of cranes, each lift choreographed to avoid twisting the structure under its own weight. Assembly teams worked from both ends, bolting latticework trusses together while suspended in safety cages. Once complete, the boom was raised into position with jacks and winches. The operation spanned 3 days and drew crowds of onlookers from nearby towns. Final assembly brought together the hoist and drag cable systems, the operator's cab perched more than 200 feet above ground, and the colossal 220 cubic yard bucket. Inspectors from Bucyrus, Erie, and Central Ohio Coal signed off on every subsystem, from the walking cams to the swing gear. By late 1969, after 2 years of continuous effort, Big Muskie stood ready. Its steel frame was the product of 200,000 hours of human labor, each component a testament to the industrial ambition of its era. The Colossus was not just built. It was assembled piece by piece, by hands and machines working in concert, setting the stage for a new chapter in surface mining. A walking dragline in motion is a study in slow, deliberate power. Each stride, 7 feet at a time, unfolds with mechanical certainty, but the true scale of that movement only becomes clear when measured against the landscape the machine must cross. To travel a single mile, a machine like Big Muskie would need to complete 754 individual steps. At a top speed of 0.1 miles per hour, covering that distance required 10 hours of continuous walking, the machine inching forward at less than 2 inches per second. For crews on the ground, Repositioning a dragline was not just a matter of flipping a switch. Every move demanded planning, patience, and a keen understanding of the terrain. Despite the engineering marvel of 44 PSI ground pressure, lighter per square inch than a car tire, we of these giants posed risks no spreadsheet could erase. Before a dragline could walk across a new stretch of overburden, ground crews laid down a temporary roadbed. Timber beams, sometimes stacked 2 or 3 deep, formed a mat wide enough to cradle the 14-foot by 70-foot steel shoes. This was not optional. Even with such gentle pressure, the soft, waterlogged soils of coal country could give way without warning. A miscalculation meant the machine would sink, sometimes so deeply that recovery involved weeks of shoring, jacking, and rebuilding the ground beneath the machine. Move crews became specialists in logistics and improvisation. They worked ahead of the dragline, surveying for hidden pockets of mud and mapping out the safest route. Each timber had to be placed with care, aligned to distribute the weight evenly under the shoes. During rainy seasons, the stakes grew higher. Water pooled in the pit, turning the earth to soup. Crews doubled the thickness of mats, sometimes working through the night to keep the path firm. The cost of a misstep was measured not just in dollars, but in lost time, and the risk of damaging a machine worth tens of millions. Operators and ground crews communicated constantly, using radios and hand signals to coordinate each stride. The walking cycle was slow, but the tension never let up. Every 7-foot advance brought a fresh set of calculations, checking for shifts in soil, listening for changes in the machine's tone, watching for the telltale sag of a timber under load. When the dragline reached the end of a bench, the process began again. Crews dismantled the old roadbed, moved beams ahead, and rebuilt the path. Progress was measured in hours, not minutes, and every mile walked was a quiet triumph of planning and teamwork. The math behind these movements draws a sharp contrast with the apparent might of the machine. A 14,500-ton dragline, capable of moving hundreds of tons of earth in a single scoop, was brought to a crawl by the limits of physics and the realities of ground support. The slow-motion stride was not a flaw. It was the necessary pace of survival in an environment where the ground itself could not be trusted. For every spectacular feat of digging, there was an equal measure of patience and calculation, played out one careful step at a time. Big Muskie's bucket sits silent in McConnellsville, Ohio, a monument to a scale of engineering few can imagine. The bucket alone weighs 230 tons empty, large enough to swallow a 2-story house or hold 2 city buses side by side. On weekends, families climb inside, tracing their hands along scarred steel walls that once scraped away coal seams, and reading plaques that list numbers almost too large to grasp. Over 22 years, Big Muskie moved 483 million cubic yards of earth, twice the volume of the Panama Canal, one scoop at a time. The monument draws visitors from across the country, each person staring up at the bucket's lip, searching for a sense of what it meant to build, run, and retire a machine of this magnitude. Central Ohio Coal paid $25 million in 1969 to bring Big Muskie to life, a sum that would top $200 million in today's dollars. The investment was staggering, and expectations were high. Big Muskie was designed to outpace every rival, with a 220 cubic yard bucket, a boom stretching over 300 feet, and a frame that stood as tall as a 22-story building. The upper works rotated on a ring of 128 rollers, each one carrying the weight of a locomotive. At full power, Big Muskie drew 13,800 volts, enough electricity to light up a small city. Every aspect of the machine was a bet on bigger being better, on sheer capacity driving down the cost of coal. But the economics of mining began to shift. The very scale that set Big Muskie apart became a liability. Operating costs soared, from the crews needed to maintain the walking mechanism to the massive energy bills that came with every shift. Earlier walking draglines, built for less money and with smaller crews, often worked for 40 or even 50 years. Big Muskie, despite moving more earth than any machine before or since, was retired after just 22 years. Coal prices fell, regulations tightened, and smaller, more flexible tracked excavators took over jobs once reserved for giants. The promise of efficiency at an unprecedented scale collided with the realities of a changing industry. Analysts and former engineers still debate whether Big Muskie was ahead of its time or simply too big for the world that followed. The numbers remain: $25 million spent, 483 million cubic yards moved, a machine that pressed on the earth with less force per square inch than a family sedan. Today, only the bucket remains, a relic that outlasted the economics, the crews, and the machine itself. Visitors who stand inside its steel shell are left with the same question that faced the industry in 1991. When is bigger truly better? And when does scale become its own undoing? The last dragline giants stand silent, and their legacy endures beneath every mined landscape and in every modern machine that walks. As automation redefines industry, the lesson is clear: pure mechanical ingenuity can solve problems even digital controls cannot foresee. The walking dragline proved that scale alone is not progress. Adaptation is. In a world chasing new technology, sometimes the boldest innovations are the ones that still leave footprints. Share your perspective in the comments below.